Okay, so we were talking about Pascal and his principle. Pascal figured out and stated that when you apply pressure to a fluid in a container, a closed container, that pressure is evenly and equally transmitted to all areas of the fluid and therefore to the walls of the container. So the pressure experienced by one place on the container because of the fluid inside of it is going to be exactly equivalent to the pressure experienced by the container on a piece of the container on the bottom of the container or on the opposite side. This is a very important concept in the field of something called hydraulics. I'm going to give you an example here of a hydraulic lift. It's just something we use as tools. But this is all, hydraulics is a concept that is used all over the place. The one thing that's weird that I can think of is starfish, echinoderms. They're little tube feet. Their little tube feet operate on this concept of hydraulics, and based on Pascal's principle, to move up and down and to create that suction that keeps them on rocks so well. They use this hydraulics. So, but quickly, let's look at the math here. This math says that the pressure of an enclosed container is the same throughout the container. So if you have, so this is basically just saying this ratio always remains the same. Wherever you are in the container, the force that's being applied there over the area that it's being applied is always going to be the same pressure, okay, as another spot in the container. All right, and then, so showing you this because we can use this to solve other things. If we solve for F2, if we set up this equation and solve for F2, we get something like this. But let me show you how this is a very helpful idea. All right, so we have a hydraulic lift here. All right, we're trying to lift a car. Now, clearly a car is kind of a heavy thing to lift. And what we figured out with this hydraulics is if we connect, and if I'm a human, okay, this is, you know, this platform here that would hold this car would be a really hard thing to apply enough pressure to, you know, from underneath to lift this car. But what we figured out is if we attach this platform here to this mechanism here, if we attach them with a container of fluid, we can apply a certain force here, but that force basically gets multiplied because it's over a much smaller area. And because that proportion always has to be the same, the pressure remains the same throughout the fluid, we can multiply our force here because this area becomes very small. All right? Our pressure stays the same, but the area becomes smaller. Therefore, our force has to be bigger. All right? And so we can apply, our force is multiplied because we don't have to apply as much. So this force, sorry, I didn't say that correctly, is actually a smaller force that you have to apply here to get the same amount of pressure, because it pushes throughout this whole fluid here, and it all has the same amount of pressure, so that when we get over here, so we have certain pressure 1, and we have a force applied that's small because it's over a small area, but when we get over to here, we have the same pressure. Pressure 1 has to equal pressure 2. And therefore, because that pressure stays the same, we can make this area bigger so that we can hold the car on this platform. And knowing that, because the pressure has to stay the same and this area has to be bigger, this force has to be bigger as well, which pushes the car up. And that's the way hydraulics work. And it's pretty cool. Alrighty. One other concept about fluid pressure has to do with depth. which you'll have to understand. We'll do a few activities about this, I hope. And you guys probably already understand this. I think you've probably experienced going down to, well, even just going down to the deep end in a pool. Probably your ears feel weird when you do that. It's because of a change in pressure. You've probably also experienced going up in high elevation in a plane or even driving in a car. You've experienced this weirdness in your ears. That's because there's a pressure change with depth of fluid, all right? What we know is that pressure varies directly with depth. So the bigger the depth, the farther down you are underneath the fluid, the higher the pressure. So that's what this is saying. As depth goes up, as that number goes up, number of meters that we are beneath the surface of the fluid goes up, the pressure also goes up. And so absolute pressure is going to be calculated by taking the atmospheric pressure, because remember, we have a whole, 300 miles of atmosphere, something like that. I have to check that. Anyway, we have a very large layer of gas surrounding us, all right? And even though it's a gas, air, and it doesn't have much weight when it's small, when you have that much, it becomes kind of big. All right, so we're going to take our atmospheric pressure to find the absolute pressure on an object here on the surface of the Earth. And we're going to add to that its density times its free fall acceleration times its depth. And that is going to give the total pressure that an object experiences on the surface of the Earth.